Hello, hi, Assalamu alaikum. So now we are going to talk about regression models for rate data. Um, Previous video we talked about regression model for count data. So this is for the rate data. Not much different except that this is a count of a specific period of time or some form of denominator. So it becomes rate. So the outcome becomes rate. Okay. The link to the node and also practical note and data set will be made available down under this YouTube video. Right. So when the response count y has index, for example, population size equal to t, then the sample rate is y over t. And the expected value of the rate is mu over t, where mu is actually the expected value of y. Um, a log linear model for the expected rate has this form, the log mu over t. So this the average count over time equals alpha plus bx. If you know, um, then you can change this into log mu minus log t because it divides here, plus alpha plus equals alpha plus bx. So log mu equals alpha plus beta plus log t. Right. So the adjustment term, which is this minus log t to the log of mean, is what is called as an offset. Okay, an offset. Let's take one example here. Outcome y, which equals the annual number of collisions between trains and road vehicles. 40 million kilometers of train travel. Okay, you got trains and you got vehicle, and they um, calculate the number of collisions between trains and road vehicles. Not common, not a common sight, right? I mean, this thing happens rarely. So so the outcome y basically is a rate, and the predictors basically years since 1975. um, so they take value of 0 actually as year 1975. So when you minus 1975 with 1975, you get 0. Okay. So yes, you get this value, which is log mu bar minus log t equal minus 4.1 minus 0.0329x. You can interpret this, you can exponentiate this, the whole thing here. Okay. um, and you get equals 0.0148 times 0.96x. So the estimated rate of train accident decreases from 0.0148 in 1975, because x here becomes 0, to 0.059 in 2003, because 2003 is 28 years later. So you replace this with 28 and you see the rate decreases from 0.0148 collision to 0.0059, it means that there were about 5.9 per uh what 1000. Okay. Before that it was about 14 point 40.8 per thousand. Oh no, this is not per thousand because um I think the value here is already is in millions. So you'll have to look at the the unit, the unit. All right. So this is in million. I think so. One unit equal 1,000 kilometers. All right. One unit equal 1,000 kilometers. So 1235.9 per thousand times another thousand, then you get 1 million. So yes, that's correct. There's another example. Predict the rate of depression in school and association with the average stress score. 100 observations. Um, and You get stress, and pop is the number of students for each class as the denominator. Okay, right. So what you get there? So you got the model is log y over t um, which is equals beta 0 plus beta 1. Next one. So the log of number of depressed over populations, which is the number of population for each class, equal minus 2.239 plus 0.0208 stress. So for 1 unit increase in stress score, then the incidence rate, because the number of depressed over the number of students actually is incidence rate, right? So incidence rate of depression increased by a factor of exponentiation 0.0208 equal 1.201, 1.021. So this is also known as incidence rate ratio. It means that 1 unit increase in stress score, the rate of depression increased by 2.1%. So if the stress score is 100, then um, what's that? 1.201 exponentiate this one 100. I think something's wrong here, right? Um, Exponentiation, the log rate of depression minus 0.031. 1, 2, yep, okay. Um, right. So, um, if you exponentiate this one, yes, one unit increase in stress, then the incidence rate change by a factor of 1.021. So this one, if you got 100 here, so it means that this becomes 0.1. So you have to exponentiate 0. So you have to exponentiate 2.08. Okay, 2.08. Um, 2.08. All right. Okay. So Let me check this one. Okay, let me check about this one. I think something wrong here. Okay, the expected rate of depression. Um, Rate of depression. Yes, which is true actually, because the rate, the log of rate. Okay, the log of rate, which actually equals minus 2.39. Let's do this. Okay, let's do this. Copy. Oops. Control C. Control V. Um, Times 100. So get minus 0.31, right? So minus 0. So the log rate is so 70% of yeah, true, yes. So then you have this one, which is 0.3 uh, z- minus 0.31. So we exponentiate this one. So it means that 73.3% of the students are depressed. Okay, if they got if every one of them has got a stress score of 100. So we can convert this into log depressed minus log population equal minus 2.39 plus 0.0208 times stress. So if you um, calculate for stress equal 100, then you get this value. And if you um, have the number of populations of 200, you can plug in here. So this means the log of expected number of depressed students are 1.99. Okay, this is the log of expected number of depressed students. So the expected count of depressed is, but actually you just exponentiate this number, so you get 0.32. So this is the number of depressed students for a population of 200 students with stress score of 100. All right, statistical inference, you get the z value if you divide the regression coefficients over standard error. Model assessment, look at the deviance, the residual between the observations and model fit, and check these references: Allen Agresti and Introduction Categorical Data Analysis, regression model for count data, a vignette of count reg, and the book by Annette J. Dobson, Introduction to Generalized Linear Model. Right. So let's go to hands-on with R. Okay. So I load library Tidyverse. I load library Broom to to have a nice output, and I use library janitor to clean variable names. And I read the dataset comes in text form, txt, so I use read underscore table, and I give the column names of income, cases, and credit cards. This is the number of credit cards, and um, how many credit cards, uh, cases, income, the income, and then the credit card, and cases, What is this? What is the dataset is all about? I have forgotten. So, but actually, is they want to look at the factors related to the rate of stolen credit card, if I'm not mistaken. Okay, so for example, for these first observations, the income was 24. He has one, and then there is no stolen credit card. And for this guy, 27, one credit card, not no none stolen. 28, he got five cases and two credit cards stolen. If I'm not mistaken, I have to look at this data set again. Okay. So we use GLM, and this is the column credit cards. I think this is the number of credit cards stolen, and income as the predictor, and um, put offset as the log of cases. So this is the log of this one. All right. So you log this. That's why you got 0.00 and 1, 2, 3, 1, and log of 5 you get 1.6. um, if you don't have this one, you can always use mutate, and mutate this and use log. Okay, but for this data set, it comes with that. All right, so your it's easy for you lah. Okay. um, then this is the log rate. Log mu over t equals minus 2.387, which is the intercept, plus 0.021 times income. Use tidy to have a nice data frame output. Specify conf.int to get the 95% confidence um, of the log of rate. Then you can exponentiate um, the results. Okay, and by specifying exponential equal true, and this is the incidence rate ratio. Okay, or incidence rate. So this is the incidence rate. Okay. um if you use the function augment, so what you have is the log of rate. Okay, log of rate. So for example, for number one, so you got your equation is minus 2.387 plus 0.021, which comes from this, and for observation number one, the income equals 24. You replace with 24, so this is the log rate. Okay. If you want to predict the log of count, okay, so use the same equation, but you have to um, you have to um, minus 1.88. I think you missed something here, right? So this should be the offset. So offset is 0. Then yeah. So I think let me check if I got this. Minus 2. Yeah, I think I miss. This is the log. Yeah, no, this is correct. Okay, because this is the log rate. Okay, this log rate. But this is the log count. So you have to move the the minus log t to this side. So for someone who has the income of 65, where is it? Okay. So for example, we want to know the expected log of count for income equals 65, and then the expected count for income equals 65. Replace this value with 65, retain the log t. You can so you get 0.7554, which actually um 0.75. Okay, this guy, I think this guy 7.7544, 0.7554 is just decimal point. So it's the same with the link. Okay, the type equal link function, sorry, parameters. um so the expected count, to get the expected count, just exponentiate the log of count, right? So we look here, the log of rate 0.7554, then we exponentiate this one, we'll get the value of 2.12. And it's similar by using predict type equal response. You'll have 2.12 for observation 23, where the income was 65. This is the residual. Okay, this is the residuals. This is the residual for the expected count, and you can plot the predicted versus observed to see how far the values of the observed and the predicted. Okay, the predicted and the observed values. So use in this example, I use ggplot, zoom point, and zoom point again for expected value, and see how big the difference between the red color and the blue color. So um what else? So this is if you want to do things manually, all right? And you can specify a new data frame. For example, for income of 25, 35, 45, 55, 65, 75, 85. For the number of denominator of log 6, for example, then you'll get the expected count for this guy, right? So for more references, you can go to all this website and and have a go. All right. Okay. Thank you.